Happy New Year and welcome back to campus, so to speak. Today we will cover course mechanics and jump right in with an introduction. So this is machine learning. Administratively, reading will be from our main text, Learn from Data, chapter 1 through 1.3 sections in the book. There's the YouTube coordinates for an accompanying video should you choose to view. So what is machine learning? Well, the branch of artificial intelligence, AI, it's a scientific discipline, and in machine learning we enterprise to examine algorithms that allow computing systems to change or modify their behavior based on data. Now, this data can be derived from databases or from sensors. It really is a type of mechanized learning system. And so throughout the ages, humankind have enterprised to try to unlock and uncover the secrets behind how we think. And machine learning is one of the methods that we devised to craft algorithms or programs for mechanized computation to try to mimic aspects of human learning. And so when we look at machine learning in the wild, then in this figure we have two rows. There's the top row going across and the bottom row going across. And if we take a look in the upper left-hand corner, we have web pages. And let's consider what a web page is. A web page is a so-called semi-structured document. It consists of text, it consists of links, it consists of rich media, such as video. And these web pages, those would serve as our data, and this data is abstracted in the form of a graph. Now, in this graph, the nodes represent the documents themselves and the content of the documents, and the edges represent the hyperlinks that reference one document from another. And so abstracting as a graph, an algorithm is run over them, specifically the PageRank algorithm. You can find early versions of it. What Google's currently using now is their corporate secret. But nonetheless, what this PageRank algorithm does is it takes the content and it computes a probabilistic graph. So it's going to take some edge weights as probabilities, and it's going to examine the degree across nodes going in this graph and reweight them. And so the idea here with PageRank is that the number of edges that point to you, your in degree, have something to do with the relative importance. And so the PageRank algorithm then takes this probabilistic graph, computes a PageRank based on the relevance and the importance of the page as defined by a statistic over the degree disparity in this graph, or how the in degree plays out across this graph. And so the end result application is a web search, i.e. the relevance ranked list of documents pertaining to some content need that is specified through an interface. So here we have our data. We have some sort of model for learning, and that's both a mathematical representation as well as an algorithm that operates on that mathematical representation. And then we have an end application. So let's take this example down below. We have sensors on an autonomous car, things such as the range, the speed, the position, and we also have video. Now, of course, we take live streaming data coming in from these sensors, and these are in time, a temporal stream, and we compute statistics over this stream to detect various events that might be occurring. Now, some events might correspond to obstacles, other events might correspond to the roadway. So, for example, in so-called lane finding, you're running various transforms over this video data to try to extract the lines and find the equations for the lines for the edges of the lane so that you can keep in the center of the lane for autonomous driving application. And so here we have our data, the sensor data. We have our learning model. This is streaming data in time with a bunch of operators or statistics operating over these temporal streams. And the application is things like collision avoidance or lane keeping, for example. And so In both of these cases, we have our data, we have some mathematical representation and operators over that mathematical representation, and ultimately that leads to some application. So this is machine learning in the wild. And so what we're going to do over the course of this semester is look at all of those things, the data, how you represent data, mathematical models, and how you operate over those mathematical models to give rise to this idea of a mechanized computation that adapts its behavior from percepts, from data. And so the required text for the course is Learning from Data by Yasser Abdel Mustafa. It's an excellent book. It's a small book, and we'll be using this supplemented by readings from the research literature. The other required textbook is MATLAB Student Edition, the latest version, 2020B, is available to you at no cost to you through the site license, and information on that is on the course Blackboard site and course resources. So please make sure you get both of these. Learning from Data is not an expensive book, but it will be required for the course. Assessment. And so class, since you're here, it meets 4:30 to 5:45, so don't need to talk about that. And we are online. We'll be meeting in my WebEx meeting room for the course of the semester. Office hours will be 10 a.m. to 11 a.m. and 11 a.m. to noon, subject to change. The work distribution, it will be absolute grading. One exam in the middle of the semester worth 15% of the grade. 3 projects, each worth 10% for a total of 30. 3 homeworks, each worth 10% for a total of 30. Class participation, 5%. And the final project is worth a total of 20%, split between the system and paper experiments, 15%, and 5% is the presentation. And so the subjects that we'll cover in this course, the learning problem, feasibility, linear model, error and noise, training and testing. We'll look at generalization of formal definition, what it means to learn outside of the samples that you have. We'll look at complexity measure, how difficult or feasible learning is. Bias variance, which is an alternate formulation for the difficulty of learning. We'll examine more complex linear models, including neural networks. We'll look at overfitting, which is a mixing problem that leads to poor performance of your learning system. We'll examine regularization, how you fix that. We'll look at model validation. We'll look at model validation, which is how you evaluate the out-of-sample performance of your model. We'll examine kernels and support vector machines, kernels in particular, a clever way of changing the representation feature space. We'll look a little bit at Bayesian methods and expectation maximization, look at some practical considerations, and of course, readings from the research literature. So when we group all of these subjects together, the first 3 talks about what learning is. It serves as an introduction. The next few, fourth through error noise, through bias variance, will look at complexity analysis. What can be learned, and is learning feasible? Then we'll look at strategies for improving upon learning, strategies for optimization. That's linear models, more advanced through kernels and support vector machines. And then we'll look at overarching frameworks, what we can do with all of these, and insert research literature, readings from the research literature throughout as well as at the end. So let's take a look at what is machine learning. So first, to ask the question of what does it mean to learn? What does it mean to you when I say something has learned? Well, for some of you, it could mean that you uncovered some patterns. In others, you were able to improve your performance, or you were able to apply knowledge outside of the scenarios in which you acquired that knowledge. So what exactly does it mean to learn? Well, let's take a look at an example, the Netflix Prize, which was a few years ago. And the goal of the Netflix Prize was to implement an algorithm that predicts movie ratings. And the open challenge was to try to come upon a 10% improvement over the algorithm for predicting Netflix movie ratings from what was in place at the time. And if you could give a 10% or better improvement in the accuracy of the ratings predictions, you get $1 million. And so somebody solved it, but this just points to necessary ingredients for learning. And they're threefold. First, a pattern must exist. If there's no underlying pattern, or as I'll call it more correctly, if there's no underlying regularity or pattern within the data, and then learning is never going to happen. It's never going to work. And so a pattern must exist. And if you think about the Netflix rating prediction, well, somewhere there's a formula, if you will. You just don't know what it is, but there's some scheme to how you rate a movie. It's just that you don't know what that is. And that leads to the second ingredient for learning, is that you can't already be able to express that pattern mathematically. Otherwise, why do you need learning? So if you have a mathematical expression for that pattern, then just implement the mathematical expression. You don't need learning. But where you need learning is if the pattern does exist, but you don't know how to express it mathematically. And of course, the third key component is you have to have data. With no data, you can't really do any learning. So let's take a look at the data representation for the Netflix prediction problem, the Netflix prize. You have a vector of scalars called your viewer vector, and each position in the vector is a real value, and the value itself corresponds to the amount of preference that the particular viewer for movies in the customer base for Netflix, the amount of preference each user has for a particular genre or actor or content type. So for example, in this first cell or position in the vector, we have, does the person like comedy? If the value is very small, we illustrate that with a small circle. If the person really likes comedy, then we'd indicate that with a much larger circle representing a larger scalar. And so each one of these scalars is going to depend on the preference for certain types of content, actors, etc., for each one of the viewers. So let's say if you really like action, you prefer blockbusters, maybe you don't really like Tom Cruise that much, so that circle or scale is going to be small. So you can imagine this vector could be quite large, given a lot of genres and a lot of actors and actresses. Then for the movie representation, each movie is represented by a corresponding vector of the same rank in d dimensions. And for the scalar values for the movie description, each one is a real value that represents the amount of certain types of content or appearances of an actor. So for example, in this first position, that still represents comedy, but if the scalar is very large, that means the circle is big, how we visualize it, it would mean the movie has a lot of comedy content. And so we do that for all of the genres and the actors, and there's a one-to-one correspondence between the viewer preference vector and the content vector describing the movie. And so here we have a vector x, and x sub v is the viewer preference vector in d dimensions. So we have xv1, xv2, xvd. And then we have xm, which is our vector corresponding to the movie content. So xm1, xm2, up through xmd describes the content of the movie. So then, if we were to compute the rating, we'd take our viewer vector, the inner product between the viewer vector and the movie content vector, and the idea is that if there is a high degree of coincidence between the preference of the viewer and the content of the movie, well, that inner product, that projection, is going to be larger. And so the rating then in this model for this representation of viewers and movies is this going to be the inner product between the viewer vector and the movie vector. Okay, and so that is our rating, and that's not really learning. It's just the coincidence measuring how much the viewer's preference matches the content of the movie. Because it makes sense. If the movie's content matches your preference, you're going to have a higher rating than if it did not match your preference, because no one likes a movie that has content that they do not enjoy. So What the learning problem corresponds to is trying to figure out what type of viewer is going to like what type of movie. So essentially, what we need to do is reverse engineer the rating. And in doing so, what we're trying to decide is what combination of factors, the individual attributes of the viewer, is going to be a good predictor of a certain type of rating for a given movie. And so what you can do is generate a large number of random vectors. And so you have some movies, you have some viewers, actual data, and you're going to augment that with a large number of fake movies and viewers, so to speak. You're just going to randomly select vectors of viewers and vectors of movies. And you're going to include in this, with these randomized movies and randomized viewers, a large database, hundreds of millions of actual data, and you're going to make a comparison between the random data and the ratings associated with real movies. And so here we have a rating, R, and that's the rating. Let's define XV prime to be the randomized viewer and XM prime to be the randomized movie. So these are just randomized. And of course, if you took the inner product between the randomized things, the ratings are just going to be all sorts of values that have no meaning relative to the real ratings. So then what we do, up top, we have the rating R prime corresponding to the inner product between the randomized movie and the randomized user. And then we take one of a large number of real movies and real users or viewers, and we look at the actual rating associated with that. So then what we do is we say, okay, well, I want to adjust this sampled viewer and this randomized movie. I'm going to adjust its factors such that the rating R prime between the two is going to get closer and closer and closer to some real rating that I select out of the database of hundreds of millions, large number of real movies, real users, and the real ratings. And so what that's doing, it's incrementally adjusting my randomized choice to more closely mimic and actually get right a real rating. And in doing so, it's finding what alternate combinations of user preference and content of movie can produce the same rating as an actual rating in the database. And if I do that a large number of times over hundreds of millions of actual ratings corresponding to users and movies, I can actually learn the right or appropriate set of combinations of factors that result in a high rating. And so I'm using actual ratings as the target for adjusting the factors that start out randomized a large number of times based on actual ratings that are in the actual database of ratings. And so this approach was actually done, or something based on this, and to win the Netflix prize. So this sort of solution actually works, and what you're doing is taking a large number of combinations of factors, or uncovering a large number of combination of factors that lead to actual ratings. And so you might have maybe a certain amount of action, a certain amount of blockbuster preference goes with a certain amount of Tom Cruise, always produces a rating of a certain value. And so you're learning all these combinations by reverse engineering what the factors should be, but those factors start out as completely randomized. Okay, so let's take a look at some of the ingredients for learning with another framing example, the credit approval problem. And let's assume that you're a large bank and you're trying to build a system to decide whether or not an applicant should be extended credit, be that a mortgage application, car loan, or what have you. So you fill out an application, and there are all sorts of questions and pieces of information you specify on that credit application. Your age, your gender, annual salary, the number of years in residence. Well, that makes sense because if you've lived someplace longer, you're more likely to satisfy your obligations. You're not just going to pick up and leave and disappear. the number of years in a job. If you've been in a certain job longer, you have a larger or longer track record for salary, and you're more likely to satisfy your obligations. Current levels of debt, if you have a lot of outstanding debt, you have more of your money used to pay for that debt instead of the new loan, so you're less likely to get it. So those questions make sense. So you take all of these descriptors, all these values, and together the vector of each of these values together represents a particular user. So you might have one user x1, and that's a vector with certain instantiation of these attributes: age, gender, salary, years in residence, and so forth. And then you have another person comes along to the bank, x2, that's another unique set of values describing collectively that particular individual, number 2, the bank's customer. And so one of the things that you're going to do then is build a system, credit approval system, and it's going to input the vector of values that collectively describe a particular applicant and output in either an approval output or denial output. And so that's going to be used as the basis for whether you should approve this particular person for credit or not. So why would you want to use an automated system to do this? And why would you not want to? Well, certainly you might want to do it because the system won't introduce biases. It's going to use all the criteria here in the same way to make a decision. Now, cases where you would want to use it also have to deal with federal law. So if you are denied credit, the lender is required by law to furnish the reason why you were denied. So they could say, oh, well, your salary was too low, your years in residence wasn't long enough. Another reason why you might not want to use it is because you could have somebody, for example, that looks like a bad risk. Maybe their salary is really low and the years of residence is really low, but their family has lived in that area for several generations, and you know that they're very reliable people and they're not going to default on a loan. So you could have someone who, these judgment calls who might not look good on paper, but who are actually good risks for the lending institution. And so you can't make those qualitative judgments when you're dealing purely with an automated system. So there are reasons why you would want to, and reasons as well, conversely, that why you would not want to use automation for this type of problem. But nonetheless, we have your input, and you have your credit applicant data in D dimensions. And so each one of these vectors, X, has D features. Each one of the features is one of those attributes culled from the application. So you're going to have a dimensional vector in D dimensions, and each dimension represents the projection of this vector along each one of these dimension axes, and these dimension axes represent one of these attributes that you would use as descriptors collectively for that particular user. And so each user looks like a point in D-dimensional space. It's called feature space. And you have the outputs, either an approval or denial output. And we'll call this approval denial as being the set Y. So Y is a so-called binary decision problem because there are two different outcomes, approval and denial. We also have something called a target function. And the target function inputs as its domain a point from this D-dimensional feature space representing vector X for each of the users, and it associates it with one of these approval or denial outcomes or outputs. And so the target function is a function that maps between the credit applicants and the approval denial output, the result of the credit evaluation. So this target function is the ideal approval formula. So lurking out there somewhere is a credit approval formula, but you don't know what it is. But it's certainly out there working, assigning labels or outputs to each one of these candidates. You also have your historical customer records, and that's going to be your data. These are the so-called label instance pairs. And they're called pairs because it's the pairing of a label, your approval or denial outcome, and there are two of them. The approval, that might be your Y for approval, and your denial, your Y in this set, big Y, for your denial. And so here for each input vector, x1, x2, that represents the first customer, the second customer, third customer, and you have big N, many of them from your historical records for your bank. Maybe that goes back 10 years, maybe it goes back 100 years. But each one of these x's is a customer or point in D dimensions represented as D many attributes that collectively describe a single customer from your historical data. Now, associated with each customer is an approval or denial. So maybe Y1 was approval, right? We'll say +1. Maybe Y2, that was the label or the outcome assigned to customer 2. Maybe that was denial. We'll call that -1, and so forth. So we have these label instance pairs, and these are your historical customer records. So then we have this next piece. This is called your hypothesis set. And your hypothesis set is a set of functions G or a class of formulas, and these are going to be employed in order to try to approximate this unknown target function. And how you evaluate whether or not this hypothesis approximates the target function is by looking at the performance of a particular hypothesis at the moment, the so-called working hypothesis, on this example historical data. And so you're trying to select a hypothesis that most closely coincides with the target function on the historical data. And when you find that hypothesis, you output the best one, call it G, and that's going to be your quote-unquote learned function, your approximated function. And so let's put them all together into a system. We have your unknown target function, F. That's your ideal credit approval function. You have your training examples consisting of your label instance pairs from your historical records, historical data. And then you also have your hypothesis set. These are your candidate formulas. And you have this other piece called your learning algorithm. Now, the learning algorithm we didn't talk about, but the learning algorithm's job is to search through this set of hypotheses for some working hypothesis that best approximates the performance or the assignment of these labels Y to the training data. And so here we're trying to measure the coincidence of each one of these hypotheses, the coincidence with the labeling or the outputs assigned by the ground truth target function, which is unknown. And so what this learning algorithm's job is then is to search through the set of candidate hypotheses for that best hypothesis, we'll call that G, our final best hypothesis, that most closely coincides with the labels that the ground truth target function has assigned to the historical data x1 through x big N. And so when we output this final hypothesis, we call this final hypothesis G. It approximates F, or the best approximation within this hypothesis set. And this is our so-called learned credit approval formula. Now, of course, I've coded these in different colors. We have some boxes that are red and some that are black. Well, the red boxes are things you have no control over. You have no control over the unknown target function. It's just there doing its job. You have no control over the training examples. Historical data, the customers, they just walked into the bank. But you do have control over those parts of the anatomy of a learning system that are in black here. So we have control over the hypothesis set. You decide what that family of functions is. You can make it really big, or you can make it very small, really specific. You decide the learning algorithm, the way in which you're going to search for the hypothesis set, and indirectly you also have control over the final best hypothesis because that's a consequence of how the learning algorithm performs its search. So this is the anatomy of a learner, and we're going to refer back to this throughout the course of the semester. So the solution is found by search, and essentially your learning algorithm is searching within this hypothesis set, this family of functions, for the best function in the hypothesis set. It does a search. So the hypothesis and learning algorithm together has a special name. This is called your learning model. The hypothesis set is the family of functions, and the learning algorithm is that component that's going to do the searching through that hypothesis set, trying to find and resulting ultimately in the final best hypothesis. So let's take a look at some example learning models, and this consists of, as we said, a set of hypotheses and a way of searching through that. So neural networks. What is a neural network? It's a specialized set of hypotheses, which are just weighted combinations passed through compositions of functions again and again and again. Now, we specify them in a graph-based format, but this is just a certain stylized class of functions. There are neural networks. Now, backpropagation is the algorithm that you use for finding the best weighted combinations in this family of weighted combinations through compositions. Support vector machines. It's a type of optimization framework for max margin subject to correct classifications, and quadratic programming is the way that you search through it. Decision tree. It's a category of model based on splits in data relative to values of features. And gain ratio is the algorithm that you use for searching. Multi-frontier optimization is a way of specifying a problem. Genetic algorithms is how you search. Regression is a linear model that's used for predicting real-valued quantities. Stochastic gradient is a way that you search. Bayesian networks is a probabilistic model that's based on conditional dependencies, and that's a type of family of functions. And belief propagation is how you update these probabilities. It's how you search through the space of possible conditional probabilities. Latent variable statistical models is a particular mathematical formulation of functions, and expectation maximization is how you search through them. Markov chain Monte Carlo is a particular graph-based probabilistic model, and Metropolis-Hastings algorithm is how you search through those probabilistic models. Latent Dirichlet allocation is a type of mathematical model, and Gibbs sampling and expectation propagation is how you search through that model. So for various types of learning models, again, we see the combination of a family of functions and a method for searching through that family of functions for the final best hypothesis. So let's take our example and carry it forward. So we have our credit score. So let's define our vector x in d dimensions to be the attributes that describe a customer. So we have x vector has d positions, so it's a point in d-dimensional space. Let's define t to be a threshold or score, and this is the litmus test associated, or the threshold associated with approval of credit. And so let's assume in a linear model, we're going to take a weighted combination of each one of these attributes describing the customer. And so if we have d many attributes, we're going to have d many weights, w1 through wd. And so for this weighted combination, what we're going to do is we say the weighted combination of each feature. So we have our sum for I goes from 1 to d of wi xi, each one of these weights, times each one of these features. We sum together those products. There's our sum. The sum I goes from 1 to d, wi xi, and we check to see whether or not it's greater than our threshold t. If it's greater than threshold t, we approve credit, and we deny credit if it's less than our threshold t. So we can absolutely rewrite this in functional form. And this functional form is going to be our hypothesis, and this hypothesis is going to be drawn from a family of hypotheses, namely our hypothesis set. So how would we rewrite this? Well, we can rewrite this by taking this expression and we subtract t from both sides of the inequality. So if we subtract t from both sides of the inequality, what do we get? We have our weighted sum, I goes from 1 to d of wi xi minus t is greater than 0. All right, so that's what we get. And likewise, we say less than 0 for denied credit. So now we can do this in functional form as our hypothesis. We'll call that h of x. Now here, we're going to use sine, S-I-G-N, not sine, the trigonometric function. But what sine is going to return is going to return a plus 1 if the parameter to sine is greater than 0, and it's going to return a minus 1 if the parameter to sine is less than 0. And so with this, if we have the case where we approve credit, that's the sum wi xi minus t greater than 0. So sine is going to return plus 1. And otherwise, we deny credit, sine is going to return a minus 1 because this quantity is going to be less than 0. And so this is a functional form, closed form for our hypothesis, and we can put them all together, and each choice of our weight vector W is going to be a uniquely different hypothesis H. And so we're going to clean this up a little bit. And so we originally had, as I said, when you subtract t from both sides of inequality, you have the sum I goes from 1 to d of wi xi minus t. And we said if it's greater than 0, we say it's a plus 1, right? That's going to be our approval condition. If it's less than 0, that's going to be our denial condition. So what we're going to do is we're going to take this minus t, and we're going to replace that with a constant we're going to call w naught. And so we're going to do that, and we're going to say sine, our weighted sum, I goes from 1 to d wi xi plus w naught. We're going to absorb that minus t in our w naught. Now, it doesn't matter since w naught is a scalar. It can absolutely be a negative value. So now, after we do that, we get the following expression. Our hypothesis h of x is sine, our weighted sum, I goes from 1 to d wi xi plus w naught. So now we're going to make another modification. We're going to include or add in a dummy variable x naught, and x naught is going to be fixed to a value of 1. Now, of course, 1 is multiplicative identity, and 1 times anything is just itself. So we can rewrite this as being 1 times w naught, which is the same as saying w naught times x naught. So if we do this, we get this expression. We have our weighted sum. I goes from 1 to d wi xi, and we have plus w naught x naught. Okay, so now that we do that, we make an observation. We say, hey, wait a minute. We have a w and x here for each term. Here's a w and an x. So we can absorb all of this into one expression under the summation, and we have the sign of I goes from 0 to d wi xi. So we're just collapsing this or folding this into the summation, and you note we changed the lower bound of the summation from I equals 1 to I equals 0. So this represents a hyperplane, a linear model in d dimensions, and we've augmented that with dummy variables, our w naught to absorb that threshold corresponding to the approval threshold for credit, and this dummy variable x naught. And so our model itself is going to be d plus 1 dimensions. We start out with d dimensions for our hyperplane, but we add another dimension with that w naught and that dummy variable x naught. So we can take this expression and we can convert it to vector matrix form. If we have a weight vector w, which consists of w naught, or w naught, w1, and our original up through wd, and then we have our x vector, which corresponds to our dummy variable x, along with the original attributes for the customer, x1 through xd. Well, if we just take w transpose x, that's nothing more than this weighted sum. I goes from 0 to d of wi xi. So we can rewrite this expression for our hypothesis using a so-called linear model, a hyperplane in d dimensions. A hyperplane in d dimensions is what you call it after 2 dimensions, but on the plane it's just a line. Right? So here in vector form, this is just h of x, our hypothesis, is sine w transpose x, where this w vector is the augmented w vector, which started out as d dimensions, and we augmented it with w naught, and the x vector in sine w transpose x is our augmented x vector, which is our original set of features from the credit application describing the applicant, augmented with our dummy variable x naught. And so this is just the sign of the inner product between the weight vector w augmented and the augmented feature vector corresponding to the user. Okay, so this is our basic model for the hypothesis set, or rather for the mathematical family of functions for our hypothesis set. And so now we need an algorithm for searching. And this algorithm has a name. It's called the Perceptron Learning Algorithm. Perceptron Learning Algorithm. or PLA. And the PLA algorithm will search through the set of hypotheses, so it's going to select a different W vector, resulting in a search for the best hypothesis, the one that most closely coincides with the ground truth assignment of +1, -1 labels to the feature vectors for the users. And so we have our family of functions, our hypotheses, and we have our label instance pairs, our training set, x1, y1 through x big N, y big N. And we're going to take our initialization of W, you can initialize our weights randomly, and then we're going to select our misclassified example. So that means we're going to take our initialization for W, and we're going to iterate over all of the training data, compute sign W transpose X using the augmented W and the augmented X vector, and we're going to mark down those where sign W transpose X for the current working hypothesis, where the working hypothesis does not agree with the ground truth label. So each one of those will be so-called misclassified examples. And so you select at random one of the misclassified examples, and for that misclassified example, you're going to update or use it as the basis of an update to the weight vector in the following fashion. And so the weight vector, its new value, so this is the new value, is going to equal the old value plus the label ground truth times the data value. So W gets W plus YI XI, where YI is the ground truth label for that input instance, that misclassified instance, and XI is the instance itself. So let's take a look at what this is doing. So in this diagram here, let's point your attention to the frame on the left. You have Y, the ground truth label for some input instance X in historical data, is equal to +1. So that means that ground truth, this person was approved for credit. It's a so-called positive example. And here we have the vector X representing the features for that particular customer. And here we have W, the current value of the weight vector. So if we take W transpose X, this W projects on the negative side of the X vector. So that means it's misclassifying our hypothesis. This W selection for this hypothesis is misclassifying this vector as being a negative example, deny, when ground truth should be approved. So W is going to get the new value of W plus Y times X. So we have X here, and Y is positive. So if we take our X vector and we superimpose it onto the head of the W, this value in the corner here is the new value of W. So this is W, and this value, this blue vector, is W plus YX. Now, if you look at this adjusted value, W plus YX, if you take the inner product of that, the projection of that onto the X vector, well, that's going to be positive, so it corrects that misclassified example. So essentially what this PLA, Perceptron Learning Algorithm, does, it searches for a new hypothesis, a new instantiation of weight vectors that corrects for that particular misclassified example. Let's look at what happens with the converse. So here we have the ground truth label should be -1. This person should be denied credit. Here's our X vector corresponding to the individual, the applicant. Here's our W vector. If we look at W transpose X, that projection, it's on the positive side. Its hypothesis is saying H of X is equal to 1. It says you should approve when ground truth, they should be not denied. So if we take W, the new value is W plus Y, the ground truth for this example, times X. So W gets or equal to W plus YX, and Y is negative, so YX. So here we take -1, multiply by X, so this is the arrow pointing in the opposite direction. We put it on the end of this arrowhead for W, and this value, this arrow up in here, that's going to be our W plus YX, where Y is -1. And so if we do that and we take the projection of this new value of W onto X, it projects rightfully on the minus side, and h of x then outputs properly this -1. So what the Perceptron Learning Algorithm does is it corrects for a misclassified example, and it finds a new hypothesis, instantiation of W, that corrects this misclassified example. Okay, so in a series of rounds, you keep selecting misclassified points in your set of data, your so-called data points, and each time it's going to change the hypothesis to a different linear hypothesis on the plane that corrects for that misclassified example. So in this example, let's imagine this was our hypothesis, our hyperplane in 2 dimensions. This is a line on the plane, and we have a misclassified point here. After one update with the PLA update rule, it's going to select a new hypothesis that's going to be on the opposite side of this point, making it a correctly classified point. Now, of course, when you move this hypothesis, in pursuing the correction of a single point, you might do damage to something that was already correctly classified. So in essence, this so-called line forms a boundary between the points that are ground truth plus outputs and ground and negative outputs from the perspective of the hyperplane. And so the hyperplane is your prediction, but the ground truth plus and minus, that's what's assigned by the target function. So you're trying to find some function, some line on the plane in this example that coincides with ground truth. And so in essence, this line forms what's called a decision boundary. It decides what the output or label should be, predicted label should be for the input data. And the idea is if you can get one that coincides with the ground truth target function, then when you get new points that aren't from the historical data, it'll also be correct. And so this decision boundary moves under PLA, our search, in order to correct the model for incorrect or misclassified data points. And the hope is that what you learn from the existing customers will also apply to the new customers, the new points that come along. So this is the PLA algorithm. But is that it? Yeah, well, essentially, but there are a lot of questions associated with this. How many rounds do you perform this update? Will it stop? Will this work for any kind of problem? Now, we talked about a line on the plane, but how do you choose your hypothesis set in general? How do you choose the algorithm? How much data do you need? There are lots of unanswered questions, and that's the subject for the course this semester. The physics of learning, the choices you make, how they impact what your model can do, how you validate it, and understanding the natural competing tensions between the various components in the anatomy of a learning model, a learning system. So let's take a look at some other stuff that's important to know. There are different categories of learning, and you can cast them in these 4 categories. There's unsupervised learning, there's supervised learning, reinforcement learning, and other variants. And so in supervised learning, you are given the ground truth output, and that's just like this credit example. And one of the examples they give in the book is a vending machine. And with this vending machine, let's say you're going to categorize coins based on the size as well as the mass. And so if you look at a U.S. quarter, a U.S. penny, a U.S. dime, and a U.S. nickel, a dime tends to be smaller in size as well as lighter. A penny, 1 cent, is a little bigger than a dime, and it also has higher mass. If you look at a nickel is even bigger than the penny and the dime, and the 5-cent piece, the nickel, is even heavier and larger. And then the biggest one in terms of both size and mass is going to be the quarter. Now, certainly when you have actual coin values, size and mass, you're going to have some correct values, but then there's going to be variation leading to a distribution over quarters. Some are going to be slightly bigger, slightly smaller, slightly heavier, slightly lighter, and so forth. And so you have the correct output. You know what the Y value is if it's categorized as a dime, a penny, a nickel, a quarter, and you're going to have a distribution due to the variability. Now, these distributions aren't going to be very dispersed because these coins are not terribly different from other instantiations of the same denomination of coins. So what you can do then is train a linear classifier, a hyperplane, with the given known values, and then you evaluate the inputs based on the trained model. So you might have one linear hypothesis that says you're either a quarter or you're not a quarter. another one that says you're either a dime or not a dime, and then another one that says you're either a penny or not a penny, and you're either 5 cents or not a 5 cents. So you take each one of these, you train them up, and then when you insert a new coin, it measures the mass and measures the size, and then it casts it in this landscape using these lines to say, are you a quarter or not a quarter? Are you a nickel or not a nickel? And you put all these together and you get one outcome that says, oh, you are a penny, you are a nickel. And it lights up on the screen that you inserted 5 cents, for example, into the vending machine. So this is an example of supervised learning. In supervised learning, you have the ground truth label associated or output with each one of a vector valued representation of your input data. Unsupervised learning is a little different. With unsupervised learning, you have the feature vector values, the size and the mass, but you're not given the ground truth label, the ground truth output value, like a 1 cent, a 5 cent, a 10 cent, or 25 cent. So again, you have the distribution because you have variability, but you don't know what the labels are for each one of the data points. Now, for these data points, you notice here the projection along the horizontal axis, that's its size, and the projection along the vertical axis, that's its mass. Now, of course, because you have two dimensions, you can plot each coin instance as a point in two-dimensional feature space. So here we have a point cost, and so if you don't have the ground truth label, the only thing you can do is compare the feature values together. And you do that based on a proximity measurement. So literally, whether it's Euclidean or non-Euclidean measures, you take each one of these coin instances and you say, okay, what's the distance between you and all the others? And you group together those that have the shortest distance to one another, separate from those who have a longer distance from one another. And so you can group them together, and these natural groupings based on this measurement of proximity based on the feature values, those are called clusters. And so once you get a set of clusters, you then go back in and you analyze them and you give them names. And this is a natural grouping based on feature values, no ground truth labels. And this is called unsupervised learning. Next, we have something called reinforcement learning. And in reinforcement learning, it comes from the neuroscience literature based on so-called dopamine response. And essentially, you have some representation of an input, like of a board game, for example. And then you have some set of actions you can perform, and you have some output as well as a grade for that output. And so essentially what you do is you try a bunch of actions that result in an output, and you accumulate these grades, and you're trying to find the output or the action you can take that's associated with the maximum expected or probabilistic average best grade. So you try and you test out different types of outputs, and then over time, as you try a lot of things, you're going to accumulate a best grade for certain types of outputs. And so then you go back after all these trials, these randomized trials, and you select that particular output based with the best expected grade, because that's your best alternative in an infinite number of tries. And that's going to be your quote-unquote plan. And so what reinforcement learning does is it finds the best scheme for doing stuff based on this trial and error driven by the expected best grade that you get, or the expected reward as it's called. So this is reinforcement learning. It's used a bit in many robotics applications as well as some other non-robotics applications. And so let's end with this, and let's talk about why this might be interesting. And so I'm going to ask you, well, suppose you have these checkerboard patterns, 3 by 3, and let's say for the top row, we said our ground truth function outputs a -1, and for our data for the bottom row, our ground truth function outputs a +1. So suppose you were given this particular pattern, and given these training examples and the output for the ground truth hypothesis, what do you think the output should be for these training inputs? Well, you could think of a lot of different alternatives. You could say, okay, when the upper left-hand corner is black, I'm going to call it -1. When the upper left-hand corner is not black, is blank, I'm going to call it +1. Let's go with that. So if you have the upper left-hand corner Black, you saw that's negative. If you have the upper left-hand corner is blank, you can say positive. And you can think of other types of things. So in that case, if that were your scheme, you'd say upper left-hand corner is black, so your hypothesis should output a -1. So the answer is that there are many different functions that can fit these 6 data points. So the key is trying to find a function that works well outside of the training data that you have. You can almost imagine it's underspecified, right? Many different functions that you can imagine just based on this scheme. So it's a trick question, but this really points to what we're going to be after throughout the course of the semester is some way of characterizing this idea of some function that works well outside of the data that you're given. Because this example that you're presented with, this is not included with the training data. It's something outside of the data. And that's going to be our focus, this so-called outside of the data performance on new inputs, our so-called generalization error. So with that, we'll end there, and we'll pick back up on Thursday. I'll see you all on Thursday.